welcome back. So we are in the discussion for solar cells. If you recall, in the last lecture I had introduced what is solar cell and also outlined a few of the very important properties of solar cell and how the solar spectra looks like. Essentially, it's a PN junction that has to absorb sunlight and convert it into electricity. Efficiency is a very important number for solar cell. I told you that in the solar spectrum, if you look and you have to use a semiconductor, for example. So a semiconductor has a band gap. All the photons with energy more than or equal to band gap will be absorbed, but the photons with energy less than the band gap will be transmitted. They will not be absorbed, so those are wasted, right? And the idea is that there are many kinds of solar cells: silicon solar cell, crystalline solar cell, amorphous solar cells, silicon, which are cheaper but also not as efficient, but they are also good, because they are cheap. Also, the wide kinds of solar cells in perovskites and organic materials and so on. But here we will limit only to silicon solar cell with PN junction, which is widely used. Okay, so I will list down the important points that we had covered yesterday and in the last class, and also I will list down the points that we are going to study today and maybe in the next class, so that you are basically aware of the working of solar cell and some of the important things that you should be you should know about solar cell working. Okay, so we'll come to the whiteboard here. So what are the things that we had talked about yesterday? One thing is that I told you about the solar spectra. The solar spectra is like a black body, right? I told you it's like a black body here. The peak is around 500 nanometer and then it decays and becomes up to 2 micron. This is like a black body at 5800 Kelvin. This is the energy of the spectra, that is kilowatt per unit area per nanometer wavelength, right? Because if you integrate out the whole thing, then you will get kilowatt per meter square. This is around 300 nanometer, for example. I told you if you use a semiconductor of any band gap, say you are using a semiconductor whose band gap corresponds to 700 nanometer, that means EC by lambda is equal to 700, you will be able to absorb only this much of the solar spectra. You will not be able to absorb the remaining. I also told you that that doesn't mean that you have to use a semiconductor whose band gap is very small so that everything is absorbed, because that will also not lead to efficiency. I will show you why. Because there are two things that are actually very important in solar cell. One is open circuit voltage, one is short circuit current. We shall definitely come to those. So you cannot compromise on both. That's why it's not the best of interest to actually have a small band gap material to absorb everything. Okay, that is not going to help. Number two thing I told you is that of course, AM, air mass elimination 0, which is above the atmosphere, air mass elimination 1, which is at noon, and in the evening, if I told you this is the earth and this is the atmosphere. So if the sun is here, then the path length that it covers is LL, so it's 1. If it is in the evening here, then the sunlight has to cover this distance, which is more than this distance. If the dead ratio is called AM whatever, even if the ratio is 1.5, then you call it AM 1.5. These are some of the standards that are used, and of course, if this was the black body curve, then your air mass elimination will look lower than that. But there will be some peaks also here, because water vapor and other things will absorb some of the wavelengths, okay, in the longer wavelength region. Then another thing I told you is that it's a PN junction. So you have a PN junction and the sunlight has to come from the top. So if the P has to be as thin as possible, so that you don't absorb so much on the P region. You want to absorb everything on the depletion region, right? Why? This is the depletion. I told you because in a PN junction, if this is the Fermi level, only the photons absorbed in the depletion region will be swept away and contribute to electricity. The photons absorbed here and here in the neutral region will give rise to electrons and holes, which will diffuse and die away. They will not contribute to electricity. So those are useless photons that are getting absorbed here. You want to get everything absorbed in the depletion region, not in the neutral region. Okay, and the depletion region should be large. That's why, or thick. The depletion region should be wide, so that you can absorb more of the photons here. You don't want the depletion to be narrow, otherwise very few photons will be absorbed. So you want to dope the n-type light. So you want to dope it light so that the depletion can extend very high, very deep, and you want to dope this very high. The reason is you want to make it thin. I told you, right? If you make it thin, only then you will waste less and less number of photons. So you want to make it thin so that you don't waste much. But if you make it too thin, then your resistance, the lateral resistance, because you have to get electricity out, which means you need to have metal contact. You will have a metal grid on top. Okay, if you look at the top view, this is a solar cell, you will have some metal grid, through which you are taking the electricity out, metal contact. So those metal contacts, you know, will take the electricity out. So there is a resistance associated with this series as a lateral resistance. If you make it thin, that resistance will be high, so you will drop unnecessary voltage, you will waste. So you do want the resistance to be low, hence you dope it very high, so that there are many carriers. So even if it is thin, your resistance is not sacrificed. Okay. Of course, you see this metal has to be there on the top. No, they will also block some of the sunlight, so that also reduces the efficiency. Your metals on the top will block, but you have no way out. You have to give metals. So people are trying to do thin metals so that you know the light absorbed or reflected off the metal is also low. Or people try to do transparent contacts also, you know, so that sunlight is not absorbed so much in the top metal. So all these things are there. Solar cell is a vast area. Solar cell technology and physics of it is also very vast. It's not sufficient in even one course. I'm only telling you a few lectures, so we can only cover very basics. Okay. So this is one important thing, that the top layer has to be lightly doped, very highly doped, P plus, and very thin. Okay, so that your depletion is extending towards the end, and your you know, depletion, and the more of the carriers absorbed. And of course, if you recall, I keep drawing this Venn diagram, but I will repeat it again here. Only the photons that are absorbed in the depletion will contribute to electricity, because all the photons that are absorbed here will give rise to an electron. One photon will give rise to one electron in one hole. That electron will be swept away by the field this side. This is an inbuilt field, you are not applying any voltage. This hole will sweep away this side, so there will be an electricity. Because of the electron going this way, current will flow this way. Because of the hole going this way, current will again flow this way. This current is in the direction opposite to the forward bias current, because for forward bias you inject the electron this side and you inject the hole this side. So the forward bias current is in this direction, which is the ideal diode equation, and your solar cell current is in the opposite direction. Remember, if you bias the device in reverse bias, then your current will be in this direction, ideal diode current. If you bias the device in forward bias, then your ideal diode current is in this direction. Okay. So any photon that is absorbed in the neutral region is waste until at least one diffusion length here. Within one diffusion length, it can actually diffuse and get this thing, but less than after that, you know, it does not matter. So this is a photon that are wasted, so that those do not matter. I mean, those we want to minimize, right? The important terms in solar cell are, I told you, short circuit current, I will come to that, open circuit voltage, there is something called fill factor, and then there is something called efficiency. These are the four very important terms that you have in solar cell. You should know all these terms. By the end of this lecture, we will know what those terms are. Okay. What we will do here is that if you don't have to apply any bias in the solar cell. By the way, there will be a load. Okay, there will be a load on which the electricity will flow in this direction, because electrons are flowing that way, holes are flowing that way. You can actually think of solar cell like a battery, but it's not like, it doesn't store energy, it is a source of energy. You connect it to a load and it will supply electricity, right? Now what we do is that we have to solve, so I will go to a next page. So this is a solar cell, and you know, recall the continuity equation. So I will take a probably a simple case. I will take a one-sided junction, which is a P plus and then N minus. Because it is P plus, your depletion to the P side will be almost negligible. All the depletion will be on the N side only. So this is your depletion region. Okay, I will take this as say the metallurgical junction. So maybe this is the depletion region towards the N. Photons absorbed in this shaded region only will contribute. I will take, suppose this is 1, this is 0, this is x equal to 0. Okay. And this is, say, the width of the thickness of the length of the device eventually. This is suppose L. Okay, L1, this is the length of the device. Here you are gonna, you know, when you have a large field here, so the Venn diagram will look like this. So you have a Fermi level. On the P side, your on the P side you will have a very high doping. So you know, this is conduction band, the valence band will almost here, because it's very highly doped. All the depletion will extend on the N side like this, right? All the depletion will extend on the N side. So this is the depletion region. Okay, this is the depletion region, and that you know from your depletion, your PN junction classes. The P type is very highly doped, so the depletion is almost negligible. Now whenever an electron falls here, it gets swept away this side. Whenever a hole gets here, it will be swept away this side when photons are coming this way. Okay, photons are coming that way. So the photons that are reaching here will eventually lead to a, we'll assume that the whole junction is uniformly illuminated. That means all the photons are coming this way, so they will be gradually absorbed more here, less will be absorbed on the other side, but we'll assume that all this depletion region is uniformly illuminated, and the photon generation rate is suppose GOP, that is the number of photons falling per centimeter cube per second. Okay, number of photons per centimeter, it can be 10 to the power 17, 10 to the power 18, whatever, depends on the sunlight, right? So it's the number of photons per centimeter cube per volume per second. That is the optical generation rate in this particular depletion region here. Okay. So so we can, you can, because we are only talking about, you know, P plus N minus junction, we don't have to worry about the the minority injection to the p side. Of course, we are only talking about the electrons that are swept away to the n side and the holes that are swept away to the p side. Now, if you recall, you just assume that this is a p-n junction. Of course, the p side is highly doped, but we can recall the p-n junction, the continuity equation. Okay, we'll continuity equation. So let's do one thing. Let's assume that for the time being, we will not say that the solar cell is not biased. It gets self biased to the forward voltage, that is different, but we will assume that this is just a p-n junction that is biased to some voltage. Okay, it may be forward bias, it may be reverse bias, it may be unbiased, it can be anything, but I am just saying that there is a voltage here developing across the junction, which is Vj, this junction. Okay, so we just have to solve the continuity equation for a p-n junction. This you remember very well. So if you look into this, then the continuity equations for holes injected to the n side. If you actually if you forward bias this junction, for example, if you forward bias this junction, then holes will be injected this side and electrons will be injected this side. Don't worry about the light falling here now. Okay, I mean that will fall, of course, but you assume that this is forward bias. Okay, you assume that this is forward bias. In reality, a solar cell is not biased. It will self bias itself depending on the load, and it will self bias itself in the forward direction only. So we are assuming that electrons are injected this side and holes are injected this side. Okay. In that case, this electron component going to the other side is negligible because this is highly doped. The p side is very highly doped. If something is very highly doped, only the carriers from that highly doped region to the lightly doped region matters. Okay, that means your electrons coming from this side to this side doesn't matter because it's highly doped. So only holes going from here to there matter. You remember this equation? You remember the reason why I'm telling you? That comes from the p-n junction ideal diode equation. You will see that because of this high doping, the electron current coming from this side to this side is negligibly small. Okay. So anyways, so I can only talk about holes that are injected from the, I'll only talk about holes because it's highly doped, injected from p plus region to n minus region. So I can write only the excess holes that are injected, here, right? Excess holes that are injected. In reality, of course, the current will be opposite to this. Okay, because the solar cell, it will be shining light on that and so on and so forth. I'll just say that these holes are injected, so I can write the holes are minority here. When the holes come here, they are minority, they are injected here, the holes are injected here, the holes become minority here. So I can talk about the hole diffusion length in the n-type region into d square by excess hole by dx square, then minus del p by tau. This is your excess holes that is decaying with a lifetime of tau, plus the optical generation rate that is happening is equal to 0. This is your continuity equation, and the boundary condition is that at the edge of this depletion, at the depletion edge here, which is your 0, I am talking about this as 0. Okay, this as 0. At the edge of the depletion, you remember, let me draw the p-n junction profile again. If you remember, if this is your depletion edge on the n side, then your excess, and this is your baseline minority holes p and 0. Remember, this is your n-type region. So in this n-type region, your holes will be minority. Your holes are minority, and the concentration is given by p and 0. It's holes on the n side, which is 0, which is equal to ni square by the doping that you are giving there, which is nd, right? Which is nd, the doping, that n-type doping that you are giving. Okay, so that is your baseline hole concentration, minority hole concentration. This is your p plus region from where you are injecting holes. So the holes will essentially decay like this. If you remember, they will decay like this. So there is an excess carrier of hole here, delta p at x equal to 0. That excess carrier is actually the baseline concentration that you have, e to the power q vj, the junction potential by kt minus 1. This is your essentially the excess hole carrier concentration. With that, if you add this baseline, then you will get the total concentration here. Anyways, this decay happens for a long diode, it happens minus x by lp sort of thing, right? So essentially, based on this decay that is happening, you can write down the diode equation. You have to solve this equation now. You have to, in an ideal diode equation, you only have these two terms, but now you also have an optical generation term. So how you will solve with this equation, and what you will get as the solution? The solution will be say the current that is flowing. Okay, the current that is flowing because of the holes getting injected from P plus will be like the I naught, okay, e to the power q Vj by kt minus 1 Okay, this is the ideal diode equation. Whether it is a forward bias or a reverse bias doesn't matter. If you can put appropriate values for the junction value, either positive for forward bias, negative for reverse bias. This is the ideal diode equation. But the ideal diode equation, if it is a forward bias, then it will go in one direction, right? I told you current will flow in this direction. But the optical generation of carrier is happening such that, I keep telling you that an electron that is generated here will be swept to this side, and a hole that is generated here will be swept to this side. So the direction of the current flow, because this is the ideal diode equation current direction, and the optical generation, because of the photons falling, electrons going this way and holes going that way, the current is in this direction. So the current of the optical generation is opposite to the ideal diode equation. So there will be another component here which is opposite to this, and that is equal to your Q area, the optical generation rate into LP, the diffusion length of holes in the n type. Remember, this LP represents the diffusion length of holes in the n type. You remember that, please do not forget the junction shape. Okay, this is P plus, this is N minus, this is depletion. Okay, this point at 0 corresponds to this boundary, and so they are decaying here. So your you have this kind of equation you will get. This is the total solar cell equation. Now if your solar cell is forward biased intentionally, then this is your ideal diode equation that flows in this direction, and this is your the optically generated current which flows in this direction. If your solar cell is biased in the negative direction, I am just telling you negative bias, then this component, the ideal diode current, also will flow in this direction, in which case the ideal diode current flowing in the opposite direction, because it is reverse saturation current, will be in the same direction as the optically generated current. So let us put things in perspective here. Okay, let us put things in perspective. Maybe you are getting a little confused. So you have a solar cell here, okay, and this is a highly doped solar cell on the P side. No, so I will draw the Fermi level here, and you know what, this is like this, is very highly doped. So this, all the depletion is on the n side only. Okay, this is a depletion on the n side. This P side has almost no depletion. This is P plus, this is N minus, all the depletion is on the n side. So we do not know what bias you are applying or what bias develops here. Some bias will be there, V junction, but the photons that are falling and generating electrons that are swept this way, holes that are swept that way, results in a current which flows in this direction, which is opposite to the ideal diode equation if the ideal diode is a forward bias thing, right. Essentially you never apply an intentional voltage on the solar cell, because solar cells are supposed to generate electricity. If you apply voltage externally, then there is no purpose of this. You distribute solar cells to these remote villages and poor people and other things, so that they can generate electricity from the sunlight. If you tell them that, you know what, you put the solar cell on your roof, but you also have to apply voltage to get electricity, then they will be like, boss, we don't have electricity in our home, how can we apply voltage there, right. So the solar cells have to generate electricity on their own, so you cannot apply voltage. Please understand that you only have a load. You only have a load across which you connect the solar cell. This load can be your television, your TV, your bulb, your radio, whatever, your fan, whatever, air condition. This load will essentially, so what will happen is that electrons will flow in this direction, holes will flow in this direction, and the current will flow in this direction. This flowing of the current in this direction will lead the solar cell to self bias itself. It will lead itself to self bias itself in the forward mode, self bias in forward direction. Matlab, a forward bias voltage will develop across the solar cell, doesn't mean the current will be in the forward bias direction only. The net current will be actually in this direction only, not in this direction. Okay. So essentially what is happening is that, you see my point, right. So but in solution of this solar cell equation, I am using it as just a standard P plus N junction. I am solving the equation, I am getting this current expression, right. So I am getting the total solar cell current expression as I equal to I naught e to the power q v, this is junction potential that develops, minus 1 minus q a, the optical generation rate, into LP. Okay. This I naught, by the way, was q a dp by LP into Ni square by Nd. This quantity is, by the way, the baseline hole concentration there, P naught, the minority carrier concentration on the N side, right. So this is your I naught. Okay. Now this is your I naught. Don't get confused here. So okay, so essentially you have your, if you draw I versus V for your ideal diode equation, then it looks like something like this, right? It turns on, sorry, I'm a bad drawing person. It turns on like that. There's some turn on voltage here. On the reverse side, there's very little current. Eventually, it breaks down. Do you remember this? You remember this, no? Now, if I shine light, what happens? You know, this curve actually shifts down. If I shine light, this curve actually shifts down. It will eventually break, of course, at very high negative voltage, but this is your 0 voltage, okay, and 0 current is 0.0, 0, and your curve shifts down. Okay, you please observe this carefully. Okay, so this, you know, so the solar cell is operated in this quadrant. This is called the fourth quadrant. So the solar cell is operated in this quadrant. I told you many classes before, solar cell is operated in that quadrant. Okay, your forward, this is your pure forward bias without any light shining or whatever, and this forward bias, you know, is quadrant 1 where LED is operated. You have operated the LED somewhere here, so that you get, if you apply forward bias and you get light out. Okay, in this quadrant there is nothing, in the second quadrant. In the third quadrant, you operate the PN junction as a photo detector or photo sensor. We will come to that after this class, of course. Photo detector, which is almost like a solar cell only. Okay, because you apply reverse bias, or you may not apply bias, but you typically apply reverse bias. This is a solar cell. In solar cell, you actually do not apply any bias. So ideally at 0 voltage, this is your 0 voltage, right? Please remember, please look at this carefully. This is your 0 voltage, but the load will make sure that your solar cell becomes self biased in the forward direction, but the current will be negative. That means you are supplying electricity to the load. If it is in this regime, that means you are applying a voltage, you are getting current, that is not your battery. Here you are in this fourth quadrant, you will be actually, is like a supplying electricity. So you will at even 0 bias, at even 0 voltage on your device, you get this much current. Don't you get this much current? Even if you do not apply, please listen this carefully. Even if you do not apply any voltage on your solar cell, just by shining light, you get this much of electricity, because the curve has shifted. This is called photovoltaic action. Okay, this is called photovoltaic action, that you are getting electricity without applying any voltage. That's a beautiful thing. This current that you are getting at 0 voltage without applying any electricity, okay, is called short circuit current. Okay, it's called short circuit current. That means if you have a solar cell, I'm talking about a PN junction, and you are connecting it, you are shorting it. You are just shorting it without any load. No load is there, and you are shining light, sunlight. Then you will get some electricity. No, that electricity is called short circuit current. No load is there. Please remember, there is no load. You are short circuiting a PN junction. Please remember, you have a P or P plus N, maybe you are short circuiting it with a wire. No load is there, and the sun is shining. Then you will generate some electricity. That electricity is called short circuit current. That is this quantity. Okay, that is this quantity. And if you, instead of short circuiting, if you keep it open, that means you just keep it open, there is no electricity flowing there. Then if there is no electricity flowing there, if you measure the potential here between these 2 points, between the P and N junction, now you are shining light. What is the potential that is developing? You are not allowing them any electricity to flow, by the way, you are just measuring what is the potential. If you do not apply any, if you do not let the electricity flow by opening it, making the circuit open, then your current will be 0. 0 current is this point, the light shining, right? 0 current is that point. Please remember, this is your I on the y axis. So this is your 0 current. So at 0 current, what is the voltage that you are measuring when you are shining light? This point is called the open circuit voltage. This point is called the open circuit voltage. We solved the continuity equation before this. This continuity equation will be used, by the way. Okay, this continuity equation will be used to find out open circuit voltage and the short circuit current. So please remember that you are having an open circuit voltage when you are not keeping the circuit closed, matlab the circuit is open. So this is the voltage that you are measuring across the PN junction when you are shining light. If you short them, no load is there, then your current will be this. At 0 voltage, you are getting this much current. This is the quantity which is called the short circuit current. But in a real solar cell, because you will have a load, in a real solar cell you will have a load, so your point will be neither here nor here. What will happen is that your point will be somewhere here. The load will define your point, operating point, and so you will operate at some voltage. Your device, your solar cell gets operated at some voltage, say Vm, I will call it, and some current will give this point, I will call say Im. So, you know, your solar cell will operate at this point. Okay. So, you are going to actually get in the fourth quadrant where the solar cell has become forward biased itself because of the load. It gives you a negative electricity, which means electricity is actually, you know, if you look at the PN junction, although it becomes self biased, your electrons will flow here, holes will flow that side. That is the dominant current in this direction, this J. This current in this negative direction because of this shining light makes sure that your total current is negative here. Okay, it is dominating character, but the device is self biased in the forward direction. Okay. So, this is your solar cell actually, and of course, if you increase the intensity of the light, suppose you go, this is your, suppose AM 0, this is your AM 1.5, not like at the evening. If you go to AM 0 outside the atmosphere, you will probably get a higher current like this. Then you will be able to get even higher, you know, current, higher voltage, higher current probably. Okay. So, it depends on the intensity of the light, of course. This is the thing. Now, this is a short circuit current. Now, this is the open circuit voltage that you know very well. Now, let us look at this expression for the total current in a solar cell. I will keep drawing the band diagram so as to make sure that this is your P, very highly doped P type, P plus, mildly doped N type. So, all the depletion is on this side. Okay. Light is shining from the top, this is the photons. Okay. So, that is your photon that is absorbed, electron is swept to this side, hole is swept to this side, total current, the solar cell current is in this direction. Of course, the device will get forward biased, so a small current will be in this direction, but the net current is in the other direction. So, the solution to this, if you remember, was I is equal to I naught e to the power q Vj by kt minus 1, okay, minus q A area, the optical generation rate, into the diffusion length of holes. Okay. And this I naught of course is equal to q A dp by Lp into Ni square by Nd. Okay. Now, in this expression, if you set Vj equal to 0, which means what does Vj equal to 0 mean? Vj equal to 0 means that I will draw also the IV here. You know, this is your I, this is your V. Your IV looks like that. When you shine light, then your IV looks like this, right? Your IV shifts. This is your short circuit current where the voltage is 0, and this is your open circuit voltage when the current is 0. So, if you set Vg equal to 0, that means this you are putting this point where the voltage is 0, then you should be able to get the current as short circuit current. You agree? So, if you put that, then I will be equal to I naught e to the power 0 minus 1, which is 0, minus q A GOP LP. So, it means your short circuit current, this is a short circuit current now, because if you know applied voltage is 0. So, your short circuit current actually is minus, the negative sign means that the current is flowing in this direction. Okay. QA GOP LP. Of course, if you have a P and N both are sort of equally doped, or if you have a proper PN junction, this is P plus N by the way, if this properly thing, then it will be GOP, then it will be GOP LP plus LN plus the depletion which will come actually also. Okay. Depletion which will always come by the way, depletion which will come, but typically the diffusion length is more than the depletion width. So, you can assume to be this is the case. So, this is your short circuit current. So, let us concentrate on this single junction only, I mean the P plus N junction. So, and in a way you are able to get the short circuit current of Q, the magnitude is QA GOP LP. So, what does it mean? You will see that the efficiency and the power output from a solar cell is higher if your short circuit current is higher, of course, right, that makes sense, this short circuit current. So, the short circuit current is higher when your optical generation rate is high, but sunlight is sunlight. You cannot increase the sunlight arbitrarily. Sunlight is sunlight. If you have a cloud on the sky, or if you have dust particles accumulating on your solar cell, if you have rain and all this thing, then your optical generation rate will come down because the sunlight will not reach your solar cell so well. Or maybe you are putting on the roof and a bird has dropped potty, that also happens, bird crap is also there all the time. Okay, then your optical generation rate will be low. So, your short circuit current will come down, your efficiency also will come down. That is a real practical problem by the way. Okay, and you want the diffusion length to be large, like this diffusion length as in the holes will diffuse, no. Okay, so the diffusion length which has to be large. Okay, the diffusion length of holes in the N type, In other words, you know, holes will go this way, electrons will go that way, but it's a p plus n junction only. So anyways, so holes have to diffuse longer, and you will basically need a material with high crystalline quality, or you know, if you have a poor quality, then your diffusion length also will become short and your short circuit current also will come down. Okay. Next is you again come to this equation only. Okay, you come to this equation only, I equal to I naught e to the power q v j by k t minus 1 minus q a g o p l p. Now you know that this is your short circuit current, by the way, or you can, the short circuit current also you can call the photo current, I photo, because when photons fall that current comes there, right. And this I naught, by the way, is q a d p by l p. I keep writing this all the time, n I square by n d, the doping on the n d side, okay, not the p side. And I keep drawing this diagram so that you know it becomes embedded in your mind. Okay, this is a solar cell at high power, you will get this kind of thing, right. So this is your short circuit current or photo current, and this is your open circuit voltage. To get open circuit voltage, this is your I, this is your V. So to get open circuit voltage, in this expression you have to set the total current to be 0, because that is the open circuit voltage. Like the solar cell that you have, P plus N, it keeps it's kept open. It's kept open. No current is flowing, which is this point. Please remember that. So you will keep this I equal to 0, so that the current is, you know, that is the voltage at which the junction will become, the open circuit voltage will be obtained. So that is 0 equal to I naught e to the power q v j by k t minus 1 minus q a g o p by l p. I can say this is the photo current or short circuit current, whatever you say, okay, I photo or I short circuit. So if you do that, then I photo current or I short circuit current by the I 0 reverse saturation current equal to e to the power q v j by k t minus 1. So I can write v j, the junction potential that is developed, is k t by q log, natural log of 1 plus I photon or I short circuit by I 0. Okay, this is your open circuit voltage. Actually, this is called open circuit voltage. Okay, this is your open circuit voltage. So this voltage is actually k t by q log of natural log of 1 plus I photo plus I naught. I photo plus I naught. This reverse saturation current also you can call the dark current or the leakage current, because that is a reverse saturation current. That is also in the absence of light you have that leakage. So you see, for a higher efficiency solar cell or for getting higher power, you also want that your open circuit voltage is high. This open circuit voltage is high. Short circuit current also should be high. Both of them should be high. Only then you will get more power and more efficiency. One cannot be high and other will be low. That will make no sense. So for the this is open circuit voltage. So for the open circuit voltage to be high, what kT by Q you cannot change, that is 26 milli electron volt constant. What you have to do is that your photo current has to be high, which means if your photo current is high, your open circuit voltage also will become better. But you cannot control the open circuit the short circuit current so much. It depends on sunlight and other things. This dark current or this I naught has to be low, which means this quantity has to be low. For that quantity to be low, if that quantity is low, then your open circuit voltage will be high. For that quantity to be low, your ND can be high, which means the doping on this side also can be high. But doping this side is already very high. This side I said light doping, but if you give higher doping on this side also, not very high but high, then you are going to get lower dark current, and that will improve the open circuit voltage. Okay, that will increase the open circuit voltage, but that is not always true, because if you dope it high, there are two problems. A problem is that if you dope it high, this is also high, then your depletion region will be narrow, so the number of photons absorbed will be small, and so you lose out the power. The number of photons absorbed will be low. Okay, you will lose out the power. Secondly, if you dope this region also high, this is already high, then the depletion will become narrow and there will be tunneling current for high doping. Tunneling current is like a leakage current that happens because of electrons and holes tunneling from one band to another band. That will extremely increase the leakage current. That means the dark current, this quantity will not be only this quantity, there will be another tunneling current. That tunneling current will be huge, and that will make your solar cell efficiency go very, very low, because the leakage or the dark current will be not only this reverse saturation current but also a tunneling current, and that tunneling current will happen if your this side is also doped high. Okay, if your this side is also doped very high, this side is also doped very high. In that case, your tunneling current will dominate and your solar cell will not work, or it will be very low, because the short circuit current or this leakage current will shoot up. That's why you cannot dope this this n minus region very high. Okay, so you cannot arbitrarily increase this quantity, the open circuit voltage. Okay, typically for silicon solar cell, the doping on this side will be around say 10 to the power 17 per centimeter cube. Above that, you will have problem. Okay, this is very highly doped. Okay, this is very highly doped. One of the ways to actually reduce or increase the open circuit voltage is that this Ni square can be reduced. This Ni square can be reduced if you have a wide band gap material. You see, if you have a wide band gap material like gallium nitride or something, if you have wide band gap material, then your Ni will be very low. If your Ni is very low, then you don't worry about Nd. This can be lightly doped, not a problem. If Ni is very low, then your this quantity open circuit voltage will be very high. But there is a problem. What is that problem? Do you know? If this is the solar spectra, if you remember, this is around 500 nanometer. If you are using a wide band gap material like gallium nitride, whose band gap corresponds to around 365 nanometer, then it will absorb only this much light. Band gap is high, no? So what will happen is that all this area is wasted. What is the point then? You are getting a very high open circuit voltage, very high, but you are wasting all the spectra. What does it mean? It means your short circuit current will be very small. So you cannot do that. There is a problem, right? But if you do a very small band gap material, for example, you do a very small band gap material here, so that I absorb everything. So then your short circuit current will be very high, nice, very nice. Okay, very good short circuit current. But the problem is that your open circuit voltage, if you look into expression of open circuit voltage, it goes as kT by Q ln of 1 plus I photon by I dark, I naught. This I naught, I told you Q dP by Lp Ni square by Nd. If you use a very small band gap material, this Ni is very high. If this Ni is very high, then this quantity is very high. This quantity is very high, which means your open circuit voltage will be low, quite low, very low. In other words, if you go for a small band gap material, you will get better IC, but your open circuit voltage will come down because your dark current will become very high because of a smaller Ni. If the dark current becomes very high, this quantity will become very low, this quantity will become very low. In other words, open circuit voltage is loosely proportional to the band gap. If you are using a small band gap material, no, your IC will be very good, but your open circuit voltage will be terrible. If you are using a wide band gap material, then your open circuit voltage, because the band gap is large, you will get very high open circuit voltage, but you will waste the entire solar spectra, so your short circuit current will be low. So that is the trade off you have to do. Okay, you cannot arbitrarily have a very wide band gap or very low band gap. That is the trade off we have to do. So let us wrap the class here. We have discussed about solar cell, and we will end the class here, so that you can go back and you can revise what you have learned. We have done the continuity equation, and I told you how the IV looks like of a solar cell when you are shining light. The concept of open circuit voltage and short circuit current we had discussed. From the solution of the continuity equation, I gave you the expression for short circuit current and the open circuit voltage. I told you that both short circuit current and open circuit voltage needs to be high. Then you will be able to get better electricity out, better efficiency, better power out. Okay. There is always a load on the solar cell that will make sure the solar cell gets forward biased. Your photons that are shining will generate electricity that is in the direction opposite to the conventional forward bias diode. Okay. So those are the things that you have learned. We will have one more lecture on solar cell that I will discuss about the limits of this efficiency, introduce Stokely-Quasar limit and fill factor and efficiency, and discuss some practical problems and other things. Okay. So that will be discussed in the next class, and we will wrap up solar cells. So thank you for your time.